Hello guys, welcome back to my class. And this is class number 2 on topic of integration. And in this class number 2, I will cover a subtopic of integration for a simple expressions. My name is Engineer Goodluck. You can find me through my email goodluck.doubt@gmail.com, and I'm from Tanzania. So you're welcome. From class number 1, we have the general formula of integration. I talked too much about this in class number 1, so let's continue. So this general formula of integration is useful in the following type of functions. First, in this position of x raised to n is where the derivative are placed. And when we want to use this formula, the derivatives that are placed at this position must hold the following properties. First, the derivative must be of linear function, or of quadratic function, or of cubic functions, or of polynomial function, and the rest of the functions that are of the form like this that we described. Okay, now consider the following examples. This example is to obtain the original function of x from derivative 1 f dash of x, where f dash of x is equal to constant 6, and 2 f dash of x is equal to 9x raised to 7, and number 3, the value of f dash of x is equal to 7x minus 4. 7x minus 4. Okay. Let's show the solution for example number 1. We have f dash of x is equal to 6, and we know f of x is equal to an integral f of derivative of x dx. F of x, original function, is equal to the integral of derivative of the original function times derivative of x. Then f of x is equal to integral of 6 times derivative of x, where 6 is a position where represent the first derivative of the function f of x, and the value is 6. Why we place 6 at this position? Because f dash of x is equal to 6, and f dash of x where it appear in this position, and the 6 must be appear in this position. And as 6 is a constant, we take it out of an integral, because 6 does not vary with the variable x. So when we take 6 out of an integral, we remain with the integral of derivative of x. That integral is a reverse of derivative, so integral and derivative cancel each other, we remain with x. So 6 times x, what we get is 6x, and we must plus c, because when we differentiate, we get the differentiation of a constant is equal to 0. So we don't know whether we differentiate a constant or not. So accidentally, to be safe, we must place a value c to represent a constant. Okay, I talked too much about this in class number 1, so I hope you understand in that class. Okay, let's look at example number 2. If f dash of x is equal to 9 times x raised to 7, then how we can get f of x? We place at the position of f dash of x the value 9x raised to 7 is this one times derivative of x. Since 9 is a constant, we get it out of the integral sign, and we remain with this expression. Okay. By using a general formula, 9 is a constant, has no problem. We keep it out of an integral sign, but as x values is derivative of x, so we must plus 1, and then we divide by this result of passing 1 to this variable. I talked too much about this in class number 1. What do we get? You see, x raised to 7 plus 1, that is for integration, we must plus 1 at this power of 7, and we must divide by this results, and then we must plus a constant, and the result is 9 over 8 times x raised to 8 plus c. Okay, let's look on an example number 3. Our first derivative of the function is 7x minus 4. Then our original function f of x is equal to, we place 7x minus 4 at the position of f dash of x, and then is where we get integral of brackets 7x minus 4 times derivative of x. So to remove these brackets, we must multiply an integral sign and derivative of x to these variables at the same time. So when we multiply by integral, we get 7x. And the same, when we multiply by derivative of x, we get d of x. Minus, we multiply by integral to a constant 4, and then we multiply by the derivative of x. Okay, then we must get out a 7, because 7 is a constant, and we remain with integral of x, derivative of x minus 4 is a constant, we get it out, and we remain with derivative of x. And when we integrate, as we say, we must, this is of power 1, we must plus 1, and we must divide by these results. Okay, and we must plus 4, and this integral and derivative cancel each other, we remain with x, and we must plus a constant c. And the final answer is 7 over 2 times x square minus 4x plus constant. Note, If my first derivative of the function f of x is a constant k, it means the power of x in this function is 0. Therefore, we can write f dash of x as k times x raised to 0. So, how others use this technique to integrate a first derivative whose value is constant? We go through the same methods. Since f of x is my original function and I want to get back my original function from a first derivative function whose value is k, and we know x power 0 is 1. So in example number 1 in this class, we saw f dash of x is equal to 6. I don't place x raised to 0 because x raised to 0 is 1. So here I want to show how others can consider x raised to 0 in order to use the general formula of integration. Okay, as f of x is equal to kx raised to 0, where kx raised to 0 is the place where we have f dash of x, and since k is a constant, we move it out of an integral sign and we remain with the integral of x raised to 0 derivative of x, which is equal to k times we have x raised to 0. As the normal method, we must plus 1 first, and then we divide by the result that we obtain here. We divide this variable by a result that we obtain after plus 1 to this power of 0. So what we get is this one. And we must plus constant as usual. So the final answer is kx plus 3. I try to show you this because you can use as well the general formula for f dash of x that involve a constant. You are not restricted to the general formula. Why so? Because f dash of x is a derivative of linear function, and when we differentiate a linear function we get a constant. So when we integrate a constant we get a linear function, and the vice versa is true. Okay, see you later in class number 3. Thank you for listening. Consider the following function. The first derivative of the function f of x is equal to x squared minus 9 over x squared plus 9. Then I can obtain the original function from its first derivative by applying the integral. So the position where f dash of x is placed in this position from brackets to brackets is where we place f dash of x, and its value is x squared minus 9 over x squared plus 9. This one. So to solve these expressions, we must open the bracket, and when we open the bracket we must multiply by integral sign and derivative sign at the same time. So I multiply integral sign to x square. At the same time, I multiply derivative of x to x square, and minus integral sign times this value 9 over x square, and I multiply the derivative of x to this value, and finish with this one. I multiply integral with 9 and then with derivative of x. Then what we get? 9 is a constant, we get it out, and 1 over x square is a rational function. So when we get 1 over x square at the top, it means 1 over x square becomes x raised to negative 2 is this one. That x raised to negative 2 is equal to 1 over x square. This is from algebra. Plus 9 is a constant, we take it out and we remain with derivative of x. So as usual, from the general formula, we plus 1 at this. Oh, I forget to place here derivative of x. Sorry, but no problem. And when we integrate this one, we plus with 1 and we divide this variable with the result obtained after passing 1, and that was we get. And this negative 9 times after passing 1, we get like this one, and plus 9 integral of in this position is 1, which is equal to x raised to 0. That is x raised to 0 also plus 1, and we divide by this result plus constant. And finally we get x raised to 3 over 3 minus 9 times negative 1 become plus 9. X raised to negative 2 plus 1 become x raised to negative 1, which x raised to negative 1 is equal to 1 over x. That's why it become 9 over x plus 9 times x plus constant c. And thank you for listening.